Hey everybody, I'm Hannah and I'll be talking about some of the molecular mechanisms of preeclampsia. Preeclampsia is the focus of our iGEM project this year. It's a pregnancy-related disease and, unfortunately, a leading cause of death for both mother and child. The placenta is necessary for preeclampsia to develop, and there's currently no cure except for its delivery, and even that isn't guaranteed. If any placental tissue remains in the body, symptoms can persist, and some evidence shows that preeclampsia-related complications can remain long after birth. 5 to 7% of all pregnancies exhibit preeclampsia as a complication, with most symptoms manifesting 20 weeks into pregnancy. It's characterized by high blood pressure and proteins in urine, otherwise known as hypertension and proteinuria. Our goal is to develop potential therapeutics for preeclampsia using synthetic biologies and the methods we discussed in earlier videos, but first we had to understand how preeclampsia worked at the molecular level. Recent studies have shown that alterations in circulating angiogenic factors leads to preeclampsia. Yeah, it's a lot of jargon. Let's break that down a bit. First, angiogenesis. This is the process in which new blood vessels form from pre-existing ones. While circulating in the blood, these angiogenic factors regulate this process, preventing too much or too little growth. Angiogenic factors are also important to keep blood vessels healthy and to make sure that organs develop correctly. So when the amount of anti-angiogenic factors increase, it's obviously not that great for the body. It's in the name. These molecules are trying to take these beneficial angiogenic factors out of the equation. On a molecular level, anti-angiogenic factors like SFLT1 and SCNG are binding to actual angiogenic factors like VEGF and PIGF. The thing is, when the two bind together, anti-angiogenic factors don't send the signal that should be sent, meaning that angiogenic factors can't do their jobs. This leads to endothelial dysfunction, where the insides of blood vessels can't perform their job, and the body parts they supply with blood suffer by extension, ultimately bringing about the hallmark symptoms of preeclampsia. So let me make an analogy. Think of a tree growing where more and more branches and leaves sprout off of each other. These are your blood vessels. You can think of angiogenic factors as a knife that's pruning the tree, preventing over and undergrowth, and keeping the tree healthy. Anti-angiogenic factors, on the other hand, would be like a blunted knife, super similar to an actual knife, but not quite, since it's unable to do its only job, just cutting and pruning things. In the meantime, the tree is growing out of control, which means it's not getting enough nutrients to every part of it to keep it alive and healthy, which means, not to be too dramatic, but it's going to die from the inside out. So, okay, we know the bare basics of how preeclampsia happens, or in other words, its pathogenesis. Let's get a little more in detail. The placenta is necessary for preeclampsia to manifest. Preeclampsia is a very complex multifactorial disease, but most importantly, preeclamptic placentas show overexpression of SFLT1 and SCNG, two anti-angiogenic factors. The amounts of SFLT1 and SCNG are increased in the serum of preeclamptic women long before any actual symptoms manifest, and their concentrations correlate with disease severity. This has led SFLT1 and SCNG to be looked at as potential biomarkers for the disease, whether in diagnostics or in therapeutics. Today, I'll mostly be focusing on SFLT1. SFLT1 is generated from FLT1 through alternative mRNA splicing, meaning that even though both molecules come from the same gene, the mRNA strand is spliced differently in each, leading to a different amino acid sequence and thus a different protein. While similar, the two have some structural differences. Most importantly, SFLT1 is a smaller protein that can circulate throughout the blood, unlike FLT1 itself. That's actually where the S comes from for soluble. This means that SFLT1 can float around and trap angiogenic factors like VEGF and PIGF in the blood and in tissues, outcompeting FLT1 and preventing any useful signaling. In other words, decreasing the amount of free, useful, and bioactive PIGF and VEGF. Placental ischemia and hypoxia may have a role in stimulating SFLT1 expression. Women with preeclampsia exhibit less blood flow through the placenta or ischemia, meaning that the tissues of the placenta can't get enough oxygen, leading to hypoxia. Hypoxic conditions may lead to higher expression of angiogenic proteins, as demonstrated by increased amounts of HIF-1 alpha. This is a transcription factor that promotes expression of angiogenic proteins like VEGF. But at the same time, hypoxia can also upregulate SFLT1 expression. It's a fine balance, but in preeclampsia, SFLT1 induction exceeds the production of angiogenic factors, leading to something called a net anti-angiogenic state. One reason for placental hypoxia may be due to defective invasion of cytotrophoblasts. Trophoblasts differentiate from the fertilized egg early in pregnancy to form the placenta in a process called pseudo vasculogenesis. These migrating trophoblasts promote adequate blood flow through the placenta by, in a sense, enlarging uterine blood vessels. While early placental development occurs in hypoxic condition and gradually becomes more oxygenated, in preeclampsia this process is disordered due to failed conversion of blood vessels. Note the difference in blood vessel capacity on the next slide. So when you look at the preeclamptic diagram versus the normal diagrams, note that the blood vessel's capacity is much lower in preeclamptic placentas, meaning that blood flow to the fetus and to the placenta itself actually is restricted as well. Also note the cytotrophoblasts and where they're located in the normal examples, showing how key the proper invasion of cytotrophoblasts is to pseudovasculogenesis. Here you see that cytotrophoblasts have properly penetrated the myometrium and the spinal arteries. While in the placental maternal ones, you see that cytotrophoblasts actually haven't gotten that far. So what does this all cause? It causes placental hypoxia, upward regulation of SFLT1, and placental insufficiency, where the fetus can't get enough nutrients or oxygen. Ultimately, clinical symptoms of preeclampsia manifest due to maternal endothelial dysfunction. No one has pinpointed exactly what the cause of preeclampsia is. It's, again, a very complex multifactorial disease. This diagram shows pretty much everything we talked about today in a nutshell. First, the basic clinical manifestations of preeclampsia. Next, the balance between pro- and anti-angiogenic factors, in this case, SFLT1 and VEGF/PIGF. Finally, the effects of hypoxia and the role of failed invasions of cytotrophoblasts in the pathogenesis of preeclampsia. Circulation of molecules like SFLT1 has shown great promise as biomarkers, and future therapeutic strategies will likely focus on key molecules within these pathways. I hope that this video was a good primer to preeclampsia and our project, and that you all learned something new today. Thank you all for watching. Feel free to reach out to Dr. Eisen with any questions, and I will see you next video. Thank you.